Okay, in this example, I'm going to model a system of differential equations. And the example that I'm going to use is an arms race between two countries. And in these two countries, the rate of production of nuclear weapons depends on the number of nuclear weapons that are present in the other country. So the rate that, for example, the US and Russia, the rate of production of nuclear weapons in the US depends on the number of nuclear weapons that exist in Russia and vice versa. Okay, let's take a look at how we set up this sort of system. So I'm going to start up the whiteboard here. And so our problem looks like this. We're going to use two variables. So we're going to say, let's say that y1 of t, okay, is the number of bombs, let's say, we'll say the US. In the US. And y2 of t is number of bombs in Russia. Okay, so this is during the Cold War. Now, the system that we're modeling, the relationship and why they're coupled, is that dy1 by dt, the rate of nuclear bomb production in the US, is proportional to, so equals k times, so this is a proportionality constant, the number of nuclear bombs in Russia, and vice versa. So dy2 by dt equals, now we need another proportionality constant. It's not necessarily going to be the same, so I'm going to use m here, y1 of t. Okay, so here are our, this is our system of differential equations, and we can write this in matrix form. Okay, so this is equivalent to, if we write it this way, equals 0 y1 of t plus k y2 of t, just to show you how it's in matrix form, equals m y1 of t plus 0 y2 of t. Okay, so what if we put this in matrix form? Okay, what we're going to have is y1 prime, okay, y2 prime, okay, equals, and here we're going to have 0, k, m, 0, and then y1, y2. Okay, so this is our system of differential equations. Now, if you saw the previous video in the series, you'll see that this basically looks like y prime is equal to a, okay, times y. Okay, so this is a type of differential equation. Again, we're in matrix form here, where a is a matrix and y is the solution. Okay, so y is a column vector made up of y1 and y2. Okay, which is the solution to this system of differential equations. Now, we don't know what y is, but what we do is we make an assumption on the form of the solution. Okay, so assume that the solution is of the form, okay, where y is equal to x e to the lambda t, okay, where this guy right here is our eigenvalue, okay, and this whole thing we can consider as the eigenvector. And what we're trying to do is we're trying to solve for this x, and we're trying to solve for lambda. Now, how do we do that? What's the next step? Well, what we do, we are going to assume the form of the solution. Okay, so this is our equation. We're going to assume the form of the solution. We're going to sub 2 into 1 and see what needs to be true for this equality to hold. Okay, so I'm going to sub, for y, I'm going to put x e to the lambda t. So what I'm going to do here, so y prime is d by dt, okay, of x e to the lambda t is equal to, okay, and we have a, right, and then x e to the lambda t. Now, x is a constant. This is a constant vector, so it can be pulled out of this derivative. So what we have is we have x d by dt e to the lambda t is equal to a x e to the lambda t. Well, the derivative of e to the at is just a e to the at. So this becomes x lambda and then e to the lambda t, and this becomes a x e to the lambda t. And we can divide both sides by e to the lambda t, and they just cross out. So what we have is we have our eigenvalue, same problem that we had. So 1 converts when we sub in equation number 2 into it. It becomes ax equals lambda x. Okay, and we saw how to solve this problem, right? This becomes, if you bring the lambda x over to the left-hand side, we have a minus, okay, I is the identity matrix, lambda x equals 0. Okay, and we saw that if this is to have a non-zero solution, what we did was we said, okay, look, how do we solve for this? Well, what we want to do, we're going to call this a fancy a. Okay, so this problem is a homogeneous, this is a homogeneous equation. Ax equals 0. And how do you solve it? Well, typically what you do is you need A inverse. You multiply A inverse by both sides. So you got to find A inverse, multiply by both sides of the equation. Okay, well, we can do like this. Equals 0. Well, here, let me just fix that for a second. I'm just going to say A inverse times 0. Okay, so what does this mean? Well, A inverse times A would be I, right? So that'll just be Ix is just x. And A inverse times 0, anything times 0 is 0. Well, this right here, if A inverse exists, then there is no eigenvector. There is no x that's part of this eigenvector. So it's useless. It's basically saying that there are no eigenvectors. But that's the trivial solution. Okay, 0, the 0 vector being a solution is not useful. So we don't want A inverse to exist. Well, what is A inverse? Well, A inverse is 1 over, it's just the formula, the determinant of A times some matrix, which we don't care because, I mean, A can be 2 by 2, 3 by 3. We don't really care. All we care about is this determinant of A. So if the determinant of A is 0, then A inverse doesn't exist. So we want the determinant of A to be equal to 0 so that this x equals 0 is not a problem. Basically, if A inverse doesn't exist, then there is a solution other than x equals 0. Okay, so that brings us to the, if we know what A is again, it's the fancy A. So what we want here, let me just put in the other equation that we normally use. Equation number, so this basically produces a third equation here. It's the determinant. Now this fancy A is just A minus I lambda, okay, equals 0. And when we studied eigenvalues, we saw that we took this equation number 3, solved for the eigenvalues, the lambdas here, and then take each eigenvalue and sub them back, okay, into equation, well, we could say equation number 1, which is this guy right here is what it turns into, okay? We sub that back in and we determine what are the x's, okay, from this equation number 1, because that's the original problem that we solved. So that's exactly what we're going to do. Okay, so what do we have? We're going to grab our A and we're going to put lambdas across the center. Okay, so if we see, here's A over here. Okay, so A minus I lambda. So what that means, so A minus I lambda, I'm going to put, let's say this, the determinant of A minus I lambda is just, okay, so we're going to put across the diagonal the minus lambdas. So minus lambda, put the K, put the M, put the negative lambda, stick it here. Actually, we want to indicate that it's a determinant, so all we have to really do is put these vertical bars here. That means determinant. Okay, now we're going to, because it's a 2 by 2, we're going to have two lambdas. We're going to get a quadratic equation. So let's do that. Let's go in here. And so what this is just negative lambda times negative lambda is lambda squared. Okay, minus, so down products minus up products, which is m times k, and we say that we want it to be equal to 0 because we don't want the a to exist. Okay, we don't want, sorry, a inverse to exist. All right, cool. So what do we have? Well, this gives us that lambda is equal to plus or minus the square root of mk. Okay, great. So now what do we do? Well, we're going to take the lambdas. Okay, for each of the lambdas, we're going to get an eigenvector from this equation, this start equation, number 1. Okay, all right, so let's plug that in. So now we have the A, actually here, let me put, so for eigenvalue, okay, we'll start with the positive square root mk. Okay, so what is the corresponding eigenvector? Well, we're going to sub in. So we're going to put, so A minus I lambda, okay, times x becomes what? What does that look like? And it has to equal 0. So what we have is we're going to plug in for that, we're going to plug in here. Let me make this. Okay, so for the positive here, this is going to become negative root mk. Okay, and then negative root mk. Put k here and m here. Times, now x is, this is a vector, a column vector, so we'll just put x and y here. So x is the vector, and these are just to make it nice and easy to understand. These are just points. These are, x is a column vector, and xy is they're the points. Okay, this equals 0 and 0. Okay, very nice. So what's next? Well, what we're going to do, okay, what I should have done, just to kind of, well, I have the lambdas there, so that's fine. So what I'm going to do is I'm going to plug in, what I need to do is basically solve for the x in terms of y. Okay, so if let me see here. Okay, I want to relate the two to each other. So what can I do here? I can multiply. Let's see. Okay, let me try something else. I'm gonna just sub in here. Let me put my pen back here. Okay, sorry about that. Computer just froze. Okay, so I'm gonna just replace this here just to make it. I'm gonna put lambda here, like this. Let's just plug this guy in here. So what do we have? What are the equations? So let's go here. We've got this equation 1 is negative lambda times x plus k times y is equal to 0. Okay, that's one equation. And then we also have equation number 2 is m times x, right? Minus lambda times y is equal to 0. Okay, and what we want to do is we basically want to see the relationship between x1 and x2. We can choose even just one of these should give us the relationship that we're looking for. Okay, so let's choose the first one here. Basically what we're saying is that lambda x equals ky. Okay, so lambda x equals ky, or what we could do, actually, I want to solve for y. So let me continue here as y is equal to lambda over k times x. That's the relationship that we have. So our equations, regardless of what the eigenvalues are, and just solving for lambda here, is that so given y, we have this guy, and we got different lambdas that we want. So let's go y1. So now we're going to plug in lambda is equal to, we said root m k. Okay, that's our first one. And so what is the relationship between x and y? This column vector is what we're looking for. We say, okay, it's square root mk over k. Okay, and so what does that mean? What is that? Well, what we can do, if we want to bring this k into underneath the square root, what we basically need to do is we need to square it and then take the square root. So basically what we're doing is we're going square root of mk over square root of k squared, which is basically like this, k over k squared. And what we have is we cancel this k with the squared, we get square root of m over k. Okay, so that is for that eigenvalue, that's the relationship between times k times x. Oh, these are times x. Okay, so then for lambda equals negative square root mk, okay, we're going to use this equation here. So I'm going to say y2, okay, is equal to negative square root mk over, let's put k squared again, it's the same times x, and it's going to be minus square root m over k times x. Okay, so what does this mean? Well, for this eigenvalue, the vector, right, remember the vector is this x. Okay, so let's go back up to the top. We're going to grab this guy right here. You see, this is our, so y equals x e to the lambda t. Okay, all right. Okay. This is the little y that goes inside here. Okay, this is what we're doing. This is the relationship. So this vector, this x vector here, this x vector is x y in this one. I should just call this y here. Keep this nice and simple. Okay, is basically is just, if this is x, then the y is square root m over k times x. Right? So then this becomes x, and then 1, and then square root m over k. Okay, so this is a constant of some sort. It can be anything. Okay, so x can be, if I just make it a constant, that may help a little better. We'll just say a. Okay, so that's this is the x eigenvector that corresponds to this lambda eigenvalue. Okay, and then we have another one here where the next vector, again, it's x and y. This relationship is basically going to be the same thing, it's just with a negative. So it's going to be b, and then 1, and then negative square root m over k. Okay? All right, so what does this mean? If we go back, we have eigenvalues here, and now we have corresponding eigenvector. Well, this is just the x that's part of the eigenvector. If we go back again, we assume the form of the solution is y equals x e to the lambda t. So what does that mean? It means we have the particular solutions. If we go back here, we assumed y equals, okay, x e to the lambda t. This was our assumed solutions. And we found the x's and the lambdas that make this solution true. It makes the equality in our differential equation true. So we have y1. So these are the, let's put particular solutions. So particular solutions. Okay, are, so y1 t is equal to, now x in the first one was a, okay, and then 1, and then square root m over k, e, and what was the lambda in this case? Square root mk t. The other particular solution, y2 of t, is some constant, b, times this vector, this column vector, times e to the negative square root mk times t. That's the other lambda. That's the second lambda here. And so the general solution is the scaled sum. So general solution, okay, is the general solution y of t, okay, is c1. Now I'm going to bring a into this constant here, okay? So it's going to be all brought under the same constant. So it's 1 square root m over k e to the square root mk times t plus c2, 1 negative square root m over k e to the negative square root mk times t. So this is the general solution. And if we had initial conditions, we could solve for C1 and C2, okay? But I never gave any initial conditions for, what was the starting number of nuclear weapons. But anyway, the main point here, I'm going to summarize here. Let's go into, look in red. What did we have? Well, we started off, okay, with a system of coupled differential equations. Why are they coupled? Because the rate of change of y1 with respect to time depends on the amount in the other country. So y1 depends on y2. y2, the rate of change of y2 depends on y1. Okay, 0 y2 there. Okay. And so what happened? So we've got the system of coupled differential equations. We formed, okay, our matrices. We saw the form of our differential equation is y prime equals ay. We assume the form of the solution as y equals x e to the lambda t. We sub it in, okay, so we take this assumed solution, we sub it into this equation, and then we see what does x have to be and what do the lambdas have to be in order to make this equality hold true. And what happened was equation number 1 brings us back to the same problem that we've solved for when we studied eigenvalues and eigenvectors. And the way that we solve this is that we are going to, we don't want there to be just the trivial solution. We want x to be something other than 0. So for that to be true, okay, what we do is we grab this matrix, and we don't want an inverse to exist, so we set the determinant. We want the determinant of this matrix to be equal to 0. And that's where this equation comes in. And just like we did when we studied eigenvalues and eigenvectors, we solve for the lambdas, okay? Now this is a 2 by 2, so there are going to be it's going to generate a quadratic equation when you take the determinant, and there are going to be 2 values, eigenvalues, okay? And for each eigenvalue, this equation right here, x, will have an eigenvector, and this x is then put into this form of the solution to give us the particular solution. So for each, we're going to have 2 particular solutions because there's 2 lambdas and 2 x's, okay? 2 eigenvalues and 2 column vectors that will form the eigenvector. Okay, so we solved for the eigenvalues. I need to zoom out a little bit. I think it's too zoomed in here. We solved for the eigenvalues, okay, and then we sub them back in to equation 1 here, into our equation. Okay, this first equation right here. We sub them in, and when we sub them in, I just took one of them right here. I brought that over here, and I solved for y in terms of x. Okay, and then what I did was I had put different values for lambda. I have lambdas square root mk. How does y relate to x? Put lambda equals negative mk. How does y relate to x? And basically what I'm doing is, see this column vector I'm solving, I'm just going to change y, put y in terms of x. So I have, here I have square root mk times x, and then here I had negative square root m over k. Sorry, this should be times x. I realize, I see that now. This should, see, x is any number, any value, it's a constant. So I just moved it to a, actually. That's actually not bad. Okay. Okay, so what I have now is I have the 2 vectors. These are the vectors that go here for x. Okay, let me go back to red here. It's these guys right there. That's what I'm looking for. So I found them. I've got lambdas and I have the x's. And so now I can solve the particular solution. This was the form, y equals x e to the lambda t. This is my first x. This is my second x. Okay, these are the lambdas that correspond. These are the eigenvalues right here and here. And so I can sub them in. Okay, and the general solution is the linear combination, okay, so scaled sum of the 2 particular solutions. And if we want to find C1 and C2, we need initial conditions. And for now, I'm going to stop there for this, this demonstration. Okay, see you next time in math class.